on Earth, the Milky Way can look almost solid. On a clear night, its pale band stretches across the sky like a distant cloud, brightened by stars too numerous and too far away for the eye to separate. The light blends together. Distance smooths billions of points into one luminous shape, and the galaxy seems full. But the appearance is misleading. The Milky Way contains more than 100 billion stars, spread through a stellar disk more than 100,000 light-years across. Those numbers describe an immense population, but they also describe an even larger volume. Most of that volume is not occupied by stars, planets, moons, or any other solid world. It is the space between them. Begin with the Sun. Its diameter is about 1.4 million kilometers, wide enough to hold more than 100 Earths side by side. Yet the nearest star beyond the Sun, Proxima Centauri, is about 4.24 light-years away. Light needs more than 4 years to cross that single neighboring gap. If the Sun were reduced to a bead 1 centimeter across, Proxima Centauri would not sit on the other side of a room or at the far end of a city. It would be almost 290 kilometers away. Between the two tiny beads, there would be roads, fields, rivers, and entire towns, all standing in for a distance that contains almost no stellar matter at all. This is the ordinary arrangement in our part of the galaxy. A star may be enormous, compared with anything in human life, but beside the distance to its neighbors, it becomes a minute island. The galaxy is not a continuous body made from touching suns. It is a wide gravitational system in which small concentrations of matter move through far greater reaches of open space. Imagine a point halfway between the Sun and Proxima Centauri. There would be no nearby surface and no familiar horizon. The Sun would no longer appear as the broad disk seen from Earth. It would be one sharp source of light among many, with Proxima shining from the opposite direction. The planets around either star would be far too distant to see without powerful instruments. In every direction, the most noticeable feature would not be an object, but the long interval before the next object begins. Open space, however, does not mean absolute nothingness. Between the stars lies the interstellar medium, a thin mixture of gas and dust shaped by radiation, magnetic fields, stellar winds, and old explosions. Across the Milky Way, an often used average is roughly 1 atom in each cubic centimeter. That is enough material gathered across galactic distances to help form future generations of stars. Locally, in any small volume, it is an emptiness far beyond ordinary experience. The word empty, then, is a description of scale and density. It does not claim that the space between stars contains nothing. It means that matter is spread so thinly that the bright objects we notice occupy only a minute part of the volume around them. So the galaxy holds two realities at once. From far away, it shines as a coherent spiral. From within, it is a collection of separated stellar neighborhoods, each surrounded by distances that light measures in years. The glow is real. The openness is real as well. They are not opposites, but two views of the same structure. And beneath that structure waits the question that will guide us deeper. How did gravity gather enough matter to build more than 100 billion stars, while leaving nearly all the room between them unfilled? The answer begins before the Milky Way had a disk, before it had spiral arms, and before its first long-lived stars had found their places. Long before the Milky Way became a spiral of stars, the universe was almost smooth. Matter was spread with remarkable evenness across space. Hydrogen and helium dominated the young cosmos, while heavier elements had not yet been forged inside stars. There were no planets, no familiar constellations, and no galactic disk turning beneath a central bulge. There were only small differences in density, slight variations from one region to another. Those variations were tiny, but gravity did not need much to begin. A region containing a little more matter than its surroundings exerted a slightly stronger pull, Nearby material moved toward it. As more matter arrived, the region became denser, and its gravity strengthened further. Over immense spans of time, the smallest imbalances grew into larger structures. This did not happen everywhere in the same way. Some regions gathered matter efficiently and became the beginnings of galaxies and galaxy clusters. Other regions lost material to their denser neighbors and became increasingly empty. The contrast between structure and open space began to widen. The universe did not start with stars scattered inside a finished emptiness. Structure and emptiness grew together. Where gravity concentrated matter, something formed. Where matter was drawn away, space became thinner. Every rising density was matched by a surrounding loss. The cosmic web that astronomers map today still preserves this old pattern, filaments and clusters carrying much of the visible structure, with broad, underdense regions between them. Within one of those growing concentrations, the material that would become the Milky Way began to assemble. It did not arrive as one perfect cloud collapsing isolation. Smaller systems formed first and merged over time. Gas fell inward. Dark matter gathered into a much larger halo, providing the gravitational framework around which ordinary matter could collect. Early stars appeared in dense pockets, while repeated mergers and flows of gas gradually built a larger galactic structure. This early Milky Way would not have looked like the galaxy we know. Its form was unsettled. Streams of stars moved along different paths. Gas clouds collided, compressed, cooled, and sometimes formed new stars. Small galaxies were pulled apart, leaving behind stars that became part of the growing halo. The disk developed gradually as gas lost energy and settled into rotation. Rotation mattered because a collapsing system does not simply fall toward one point. Any small initial motion is preserved as matter moves inward. As the system contracts, its rotation becomes more pronounced. Gas that cannot fall directly into the center begins to orbit. Collisions between gas clouds allow some motion to be redistributed, and over time much of the gas settles into a flattened disk. Stars behave differently. Once formed, a star can pass through a diffuse cloud of gas without losing much speed. It follows a path determined mainly by gravity. Gas, by contrast, can collide with gas. It can compress, heat, cool, and radiate energy away. This allows it to settle more readily into a disk, while older stars and dark matter can remain distributed through a thicker, rounder region. The Milky Way, therefore, became layered. A rotating disk held much of the gas dusts and ongoing star formation. A central bulge contained an older and denser stellar population. A much larger halo surrounded both, carrying dark matter, ancient stars, globular clusters, and the remnants of smaller systems absorbed over billions of years. Yet even while all of this structure was forming, the galaxy never came close to filling its available space. The reason lies in the behavior of gas. A cloud may contain enough total material to produce thousands of stars, but that does not mean the entire cloud collapses at once. Gas resists gravity in several ways. Heat creates outward pressure. Turbulence moves material in irregular directions. Magnetic fields provide additional support. Rotation can slow collapse. Radiation from nearby stars can warm and disperse the cloud. Only certain regions become dense and cold enough for gravity to take control. Inside those regions, the process repeats on smaller scales. A large molecular cloud contains denser clumps. The clumps contain denser cores. Only some cores continue inward far enough to form stars. Around them remains a far greater volume of gas that never reaches the same conditions. This is one of the central reasons the Milky Way is so open. Stars are not the default form of galactic matter. They are the outcome of a demanding sequence. Gas must gather, cool, remain bound, overcome pressure, and continue collapsing without being disrupted. Most interstellar material does not complete that sequence at any given time. Even inside active stellar nurseries, much of the gas remains outside the forming stars. A new star grows by drawing material inward through a disk. At the same time, radiation, winds, and narrow outflows begin pushing material away. Massive young stars can reshape an entire cloud, heating nearby gas and carving cavities through the region. Later, supernova explosions may scatter much of what remains. Stellar birth, therefore, contains its own limit. The first stars to form begin changing the environment for those that might follow. Some compressed regions may be pushed toward collapse, but other regions are dispersed. The same process can encourage star formation in one location while ending it in another. The result is not a solid field of suns. It is a cluster of newborn stars, separated by open intervals, all embedded for a time within a cloud that is already being broken apart. Over millions of years, the remaining gas thins. Over longer spans, the stars themselves begin to separate. Many stars are born in groups, but most groups do not remain intact forever. Their shared gravity may be too weak to hold them together. Against the pull of the galaxy, encounters with molecular clouds, and the slow exchange of energy between neighboring stars, the cluster expands. Members move outward. The stars that form beside one another gradually enter the wider galactic population. Our Sun likely began this way. It probably formed with many stellar siblings inside a cloud that disappeared billions of years ago. Those stars did not remain gathered around the same center. The galaxy carried them along different orbits, and their original arrangement dissolved into the disk. What we now experience as normal stellar separation is partly the long aftermath of that dispersal. Stars form in limited pockets. Their birth clouds break apart. Their clusters loosen. Galactic motion spreads them through a much larger volume. The distances grow until each star appears to occupy its own region, surrounded by years of travel before the next one begins. So the emptiness of the Milky Way has more than one origin. Some of it comes from matter that never became dense enough to form a star. Some comes from gas expelled by the stars that did form. Some comes from the slow dispersal of stellar groups across the rotating disk. And some is built into the scale of the galaxy itself, whose dimensions are so large that even hundreds of billions of stars remain sparse within it. Gravity gathered the Milky Way, but gravity did not gather all of its matter into one place. It built a hierarchy of concentrations, galaxies within the cosmic web, clouds within galaxies, cores within clouds, stars within cores, and planets within a small number of stellar systems. Between every level, space remained. The galaxy grew not by erasing emptiness, but by arranging matter inside it. Once matter has been arranged into stars, the scale of the arrangement becomes difficult to picture. The Sun feels large because every familiar distance around Earth is small beside it. More than 1 million Earths could fit inside its volume. Its light reaches our planet in a little over 8 minutes, crossing the space between us at a speed no material object can match. And yet the Sun is only one point inside a much larger interval. The nearest neighboring star is more than 4 light years away. That distance is not merely larger than the solar system, it belongs to a different scale of space. Neptune orbits the Sun at an average distance of about 30 astronomical units. Light reaches it in a little over 4 hours. Even the Kuiper Belt, the broad region of icy bodies beyond Neptune, occupies only the inner portion of the Sun's wider domain. The distant Oort cloud may extend much farther, perhaps tens of thousands of astronomical units, though its true structure remains difficult to observe directly. Still, the distance to another star is greater. The outermost comets, loosely bound to the Sun, may travel through a region where the gravity of neighboring stars and the Milky Way begins to matter. There is no wall marking the end of a stellar system and the beginning of another. The The sun's influence weakens gradually, while the wider gravitational field of the galaxy is always present. Between these distant boundaries lies interstellar space. The word interstellar simply means between the stars, but the region it describes is the dominant environment of the Milky Way. Planetary systems occupy small islands within it. Stars move through it, light crosses it. Gas drifts through it in thin currents shaped by magnetic fields, radiation, and the history of events that occurred millions of years before. Near the solar system, the interstellar medium is so diffuse that a small container holding ordinary air would contain vastly more particles than the same volume of space between the stars. But the material is not absent. Hydrogen is the most common element. Helium follows. There are traces of heavier elements produced by earlier generations of stars, along with grains of dust made from carbon-rich and silicate materials. The dust is sparse, but across long distances, it can absorb and scatter enough light to hide parts of the galaxy from visible view. This is why the Milky Way contains dark lanes. When you look toward the galactic plane, especially from a dark location, the band of starlight is interrupted by irregular patches where fewer stars seem to appear. Those patches are not empty holes. They are clouds of dust lying between Earth and more distant stars, blocking some of the light that would otherwise reach us. At infrared and radio wavelengths, many of those hidden regions become visible. Different forms of light reveal different layers of the galaxy. Visible light shows stars that are not heavily obscured. Infrared observations can pass through some of the dust and expose warmer objects inside. Radio telescopes can trace cold hydrogen and molecules that would remain unseen to the eye. The apparently blank spaces of the Milky Way are therefore not all the same. Some are broad intervals with very little matter. Some contain thin clouds of warm gas. Others hold colder and denser material. Some are cavities heated by old supernova explosions. And within the rare molecular clouds where gas becomes cold and concentrated, new stars may still be forming. Astronomers describe the interstellar medium as existing in several overlapping phases. Some gas is hot and highly ionized, with electrons separated from atomic nuclei. Some is warm and more widely distributed. Some is cold and neutral. In the densest clouds, hydrogen atoms pair into molecules, and other simple molecules appear in small amounts. These phases do not sit in clean layers. They fold around one another. Hot gas fills cavities carved by explosions. Cooler clouds collect along their edges. Filaments stretch through larger complexes. Magnetic fields guide charged particles and influence the way gas can move. Turbulence creates knots, sheets, and irregular boundaries across scales ranging from fractions of a light year to hundreds of light years. The galaxy may be sparse, but it is not featureless. Imagine traveling away from the solar system without choosing another star as a destination. The planets would slowly become points. The sun would shrink until it joined the wider field of stars. There would be no sudden moment when the solar system ended. Its familiar architecture would simply fade behind you. For a long time, little would change. No planet would rise ahead. No neighboring sun would expand into a disk. The surrounding stars would alter their positions so gradually that the pattern might seem fixed. A spacecraft, moving as fast as Voyager 1, would need tens of thousands of years to cover the distance to even the nearest stellar systems. During a human lifetime, it would cross only a minute fraction of the gap. This is one reason interstellar distance feels so different from planetary distance. Within the solar system, sunlight provides the common center. Planets share a visible relationship with the same star. Their orbits can be drawn on one diagram, even when the true distances require careful scaling. Between stars, there is no single local map that makes the emptiness feel manageable. Every destination is separated by years of light travel. and every direct journey using present forms of propulsion would extend far beyond a human life. The emptiness is not only wide, it is enduring. An object passing through interstellar space would encounter occasional atoms and grains of dust, but not enough to resemble wind or weather. There would be no air to carry sound. Heat could not move through conduction in the ordinary way because there would be too few particles nearby. Temperature also becomes a more complicated idea. A thin gas may contain particles moving at speeds associated with very high temperatures, yet the gas can transfer very little heat because so few particles are present. A spacecraft inside hot interstellar plasma would not necessarily experience the environment as a furnace. The energy is spread across too little matter. This becomes important throughout astronomy. A region can be described as millions of degrees while remaining almost empty. Another region can be colder but contain far more material. The numbers describe the motion of particles, but the effect on an object depends on how many particles are there to make contact. In interstellar space, radiation becomes more important than touch. Starlight travels from many directions. The cosmic microwave background provides a faint radiation field left from the early universe. High-energy particles called cosmic rays move through the galaxy, accelerated by sources that include supernova remnants and other energetic environments. Magnetic fields curve the paths of charged particles across distances far larger than any planetary system. Though weak, these fields fill enormous volumes, and over those volumes, they help shape the movement of gas and cosmic rays. The space between stars is therefore crossed by influences that remain invisible to ordinary sight. Light, gravity, magnetic fields, and fast particles pass through regions where solid matter is rare. Each carries information or energy from distant events. A supernova can disturb gas many light years away. A young star can ionize part of the cloud around it. A spiral arm can compress material as gas moves through the galactic disk. The emptiness allows these influences to travel. It also protects stellar systems from one another. Because neighboring stars are so distant, their direct gravitational effects are usually weak. Planets can continue orbiting their own suns for billions of years without frequent disruption from passing stars. Comets at the farthest edges of a system may be disturbed more easily, but the inner planets remain sheltered by distance. The same separation that makes travel difficult helps create stability. Our solar system has moved around the Milky Way many times since it formed. Its neighboring stars have changed. Some passed closer in the distant past, and others will pass closer in the future. But the spaces between them remain large enough that close encounters are uncommon. This is the pattern repeated across much of the galactic disk. Stars travel on different paths, each responding to the total gravitational field of the Milky Way. They do not move as one rigid structure. They overtake one another, rise slightly above and below the disk, and pass through regions of different density. Yet most continue without collision. Their small physical sizes and immense separations leave room for billions of independent motions to unfold at once. The Milky Way looks continuous because light closes the visual gaps. Gravity holds the larger system together because every star contributes to a shared field, along with gas and dark matter. But on the scale of an individual traveler, continuity disappears. There are only distant destinations, thin material, and long intervals, where almost nothing solid is near. The next change in this picture comes as you move inward through the galaxy. The Milky Way is sparse almost everywhere, but it is not equally sparse. Closer to the center, the distance is narrow, the radiation field grows stronger, and the calm separation of the solar neighborhood gives way to a more crowded form of emptiness. The Milky Way becomes denser as you move inward, but it never becomes solid. From the sun's position, Roughly 26,000 light-years from the galactic center, the stellar neighborhood is relatively open. Nearby, stars are separated by distances measured in light-years, and the gravitational influence of each system fades long before the next star is reached. Closer to the center, those intervals begin to shrink. The broad disk gradually gives to the galactic bulge a thick concentration of older stars arranged around the inner region of the galaxy. From a distance, this bulge appears as a smooth glow. Up close, it would resolve into countless individual suns moving on complicated paths. They do not all circle the center in the same orderly plane. Stars in the disk tend to follow broadly similar directions around the galaxy. In the bulge, their orbits are more varied. Some rise far above the disk. Some plunge inward and then travel outward again. Their paths cross in 3 dimensions, producing a crowded gravitational environment without producing a crowded physical one. This difference matters. A city is dense because buildings, streets, people, and vehicles occupy much of the available ground. The galactic bulge is dense only in comparison with the outer disk. Its stars are more numerous within a given volume, yet the volume remains dominated by the intervals between them. Even here, a journey from one star to another would still be a journey through open space. As the center approaches, the background light grows stronger. More stars appear in every direction, and the distinction between night and day would change on any world with a clear sky. Some nearby stars might shine brightly enough to cast shadows. The combined glow of unresolved stars could form a permanent haze across part of the heavens. The sky would feel full. The space itself would not. Near the innermost region lies the Milky Way's nuclear star cluster, a compact population gathered around the gravitational center. Millions of stars occupy a region only a few dozen light-years across. This is one of the densest stellar environments in the galaxy. At its heart sits Sagittarius, a star, the supermassive black hole around which the central stars move. Its mass is about 4 million times that of the Sun. The black hole itself does not shine. What astronomers observe, the motion of surrounding stars and gas, along with radiation produced when matter in the region becomes heated. For decades, telescopes have followed individual stars traveling around this invisible center. One of the best studied is called S2. Its orbit carries it close to Sagittarius, a star, before swinging it far outward again. It completes one circuit in about 16 years, moving fastest near its closest approach. By tracking that motion, astronomers can measure the mass concentrated at the center with remarkable precision. The path of S2 is a demonstration of gravity made visible. The black hole cannot be seen directly in ordinary light, but the star's orbit traces the shape of the gravitational field around it. The faster S2 moves, and the tighter its path curves, the more clearly the hidden mass is revealed. Yet even during its closest passage, the star does not brush against another star. There is room for its orbit. This is the central paradox of galactic density. Near Sagittarius, a star, stars move in a region far more crowded than the solar neighborhood. Encounters are more frequent. Gravitational disturbances are stronger. Binary systems may be altered or broken apart. Some stars can be thrown onto new paths. Others may be driven closer to the black hole. Still, direct stellar collisions remain uncommon. A star is large, but its target area is tiny compared with the volume through which it moves. Two stars can cross the same central region many times without coming near enough to touch. The effect is similar to releasing a handful of grains into a cathedral and allowing them to move for centuries. Their paths may cross. Their motions may be influenced by one another. But the building contains far more air than grain. In the nuclear cluster, gravity creates complexity long before matter creates contact. A passing star can disturb a planetary system without striking it. A close encounter can reshape the distant cloud of comets. around another sun. In a binary pair, the approach of a third star can exchange orbital energy, tightening one partnership while sending another member away. These events are more likely near the galactic center because the stellar paths are more closely packed. The environment is also more active in other ways. Radiation levels are higher. Massive stars are more common in some central populations. Supernova explosions occur within a region where neighboring systems are closer. Compressed, heated, and stirred by the combined influence of stars, magnetic fields, and the central black hole, the center is therefore not only denser, it is less stable. For a planetary system, stability depends on more than the presence of a suitable star. It also depends on the larger environment remaining calm for long periods. Orbits need time to persist. Atmospheres need protection from repeated radiation events. Complex chemistry benefits from continuity. The outer disk offers more of that continuity. Our location is not empty because the galaxy failed to place matter here. It is open because the Milky Way's mass is distributed across an enormous disk, and because the Sun orbits far from the central concentration. That distance reduces several kinds of disturbance. Nearby, supernovae are less frequent. Close stellar encounters are less common. The radiation field is weaker. The black hole at the center has almost no direct effect on the solar system beyond its small contribution to the total mass of the galaxy. The Sun does not orbit Sagittarius, a star alone. It responds to the combined gravity of stars, gas, dark matter, and every other mass enclosed within its galactic path. The central black hole, despite its great mass, represents only a small part of that total. This is another way galactic scale resists familiar intuition. A supermassive black hole sounds as though it should dominate the entire Milky Way. Near the center, it does dominate the motion of nearby stars. Farther out, its influence blends into the much larger gravitational field of the galaxy. The Sun's path is shaped less by one central object than by an extended distribution of matter. That distribution is not visible in full. The stars and gas account for only part of the gravitational pull needed to explain the rotation of the Milky Way. Dark matter contributes much of the rest, surrounding the luminous galaxy in a halo, far larger than the stellar disk. The emptiness between stars is therefore crossed by gravity from matter that cannot be seen directly. A region may appear nearly vacant in visible light and still lie within a deep gravitational structure. The space is empty of stars, but not empty of influence. Near the galactic center, that influence becomes easier to note because motion is faster and density is higher. In the outer disk, it is spread across distances so great that it feels almost absent. You can sense the contrast by returning for a moment to the night above Earth. The dark spaces between the stars are part of the environment that has protected the solar system. The nearest suns are distant enough to remain points. The galactic center is hidden behind layers of dust and lies too far away to brighten the sky into permanent twilight. The same openness that makes the universe look dark also gives worlds time. It allows a planet to circle one star without constant interruption from another. It allows a moon to remain bound to its planet. It allows climates, oceans, surfaces, and atmospheres to change through long sequences rather than being repeatedly disturbed by neighboring systems. The darkness between stars is not merely an absence of light. It is a measure of separation, and separation can become a form of stability. The central Milky Way shows what happens when that separation narrows. The galaxy becomes brighter, more energetic, and more dynamically complicated. As stars encounter stronger radiation fields and more frequent gravitational changes. But the basic architecture remains. There are stars, and there is the room between them. Even at the densest point of the Milky Way, the room still wins. Beyond the bulge, Other dense environments preserve the same lesson in a different form. Globular clusters gather enormous numbers of old stars into compact spheres, carrying some of the earliest surviving stellar populations around the halo. They are crowded by galactic standards, and they too are mostly space. A globular cluster can contain hundreds of thousands of stars within a sphere only a few dozen light-years wide. Some contain more than 1 million. Seen through a telescope, they resemble rounded swarms of light, bright at the center and gradually thinning toward the edge. Their stars appear pressed together so closely that the cluster can look almost granular, as though every visible space has been filled. But the image is formed across a great distance. Inside the cluster, the stars would separate again. The gaps would be much smaller than those around the Sun, yet they would still be measured in astronomical units, light months and fractions of a light year. A traveler could move through the core and pass between many stellar systems without touching any of them. The sky would be transformed. Nearby stars would appear brighter. More of them would be visible during whatever passed for night on a planet there. Some might look less like remote points and more like brilliant beacons, scattered in every direction. The combined light could soften the darkness, especially near the center of the cluster. And beneath that richer sky, the gravitational environment would be active. A globular cluster is not a frozen arrangement. Every star moves through the shared gravity of the whole system. Some follow wide paths around the outer regions. Others cross through the core, where the stellar density is highest. Over time, these stars exchange energy. A close encounter can slightly change the speed and direction of both objects. One star may lose energy and sink toward the center. Another may gain energy and move outward. Repeated encounters gradually reshape the cluster. Astronomers call part of this process relaxation. The word suggests calm, but the physics describes a long redistribution of orbital energy. Across millions or billions of years, the cluster slowly reorganizes itself through many small gravitation interactions. The more massive stars and stellar remnants tend to move inward. Lighter stars are more easily pushed toward the edges. Some gain enough speed to escape the cluster entirely, becoming solitary members of the galactic halo. The cluster can therefore evaporate, not through heat, but through motion. One star at a time, its population leaks into the surrounding galaxy. In the dense core, close encounters can also create unusual systems. Binary stars may become tighter after interacting with a third star. A passing object may replace one member of a pair. White dwarfs, neutron stars, and ordinary stars can be brought into combinations that would be less likely in the open galactic disk. These interactions help explain why globular clusters contain so many compact binaries, rapidly spinning neutron stars, and other systems shaped by repeated gravitational exchange. Still, the stars do not need to collide for the cluster to evolve. Gravity reaches across the gaps. This is one of the clearest examples of how the Milky Way can be dynamically connected while remaining physically sparse. Objects influence one another from distances that leave almost all the volume unoccupied. Direct stellar collisions can occur in the densest cores, but they are rare compared with gravitational encounters. When two ordinary stars do meet, they do not behave like rigid spheres striking one another. They are made of plasma held together by gravity. Their outer layers can distort, mix, or be stripped away. In some cases, two stars may merge and form a single object, with more mass than either began with. Some unusually blue and bright stars in old clusters may have formed through mergers or through the transfer of material between neighboring stars. They appear younger than the population around them, not because they were born recently, but because an interaction supplied them with new fuel or combined them into a larger star. Even these rare events occur within a setting dominated by distance. The cluster may contain 1,000,000 stars, but its history is governed mainly by near misses. This becomes clearer in Omega Centauri, one of the largest globular clusters associated with the Milky Way. It contains several million stars and spans roughly 150 light-years. Its stellar populations do not all share the same age or chemical composition, which suggests a more complicated past than that of an ordinary cluster. One possibility is that Omega Centauri was once the central region of a small galaxy. As that galaxy passed near the Milky Way, tidal forces may have stripped away its outer stars and gas. The dense core remained, continuing to orbit the larger galaxy as a massive cluster. Whether every detail of that history is correct remains an active subject of study. But the possibility reveals how galactic structure can be taken apart. Without individual stars being destroyed, the Milky Way's gravity can pull an entire smaller system into streams. Stars that once belonged to one galaxy become part of another. Their paths change. Their old structure dissolves, yet most of the stars continue intact, carried into new orbits through a larger gravitational field. The same principle appears on an even greater scale when two galaxies merge. From a distance, a galactic collision looks dramatic. Spiral arms bend, long tidal tails extend into space. Gas clouds brighten with new star formation. The original shapes of both galaxies may disappear, but the stars themselves usually pass one another. A galaxy is too sparse for most of its suns to collide, even when another galaxy moves directly through it. The stellar populations interpenetrate. Each star responds to the changing gravitational field, but the physical chance of striking another star remains very small. Two luminous disks can cross while nearly every star avoids contact. The phrase galaxy collision is therefore both accurate and misleading. The galaxies do collide as gravitational systems. Their gas clouds interact. Their orbits change. Their central regions draw together, but most of the stars move through open pathways between the stars of the other galaxy. The event is less like two solid bodies crashing and more like two weather systems overlapping, except that the motions unfold across hundreds of millions of years. Gas behaves differently from stars. When the interstellar gas of one galaxy meets gas from another, the clouds can compress and heat. Some of that material loses energy, cools, and becomes dense enough to form new stars. This is why merging galaxies often contain bright regions of accelerated star formation. The merger rearranges the emptiness without removing it. New clusters appear. Massive young stars illuminate clouds. Supernovae follow. The combined galaxy may shine more intensely than either original system did alone. Yet every new star still occupies only a minute part of the available volume. After the merger settles, the resulting galaxy may contain a larger central bulge, a changed disk, or a smoother elliptical form. Its stars will follow new paths. Some will be thrown into the outer halo. Others will settle closer to the center. The structure changes. The openness remains. The Milky Way and the Andromeda Galaxy are moving toward one another, and their future interaction is often described as an approaching collision. The process will unfold over billions of years, and the exact outcome depends on their motion, mass, and the influence of surrounding matter. The night sky of a future Earth, should Earth still be present, would change dramatically as Andromeda grew larger overhead. Its stars would spread across a widening portion of the sky. Bright bands and distorted arms might become visible. Over time, the two galaxies would pass through one another, separate, and return under their mutual gravity. For the solar system, the greatest change would probably be orbital. The Sun might be moved to another region of the merged. It could travel farther from the center or follow a different path through the rearranged stellar population. A direct collision with another star would remain extremely unlikely. The future sky could become crowded with light, while the solar system itself continued through mostly empty space. This distinction between appearance and itinerary returns again and again. A globular cluster looks packed, but its stars are separated. A galactic center looks almost continuous, but most of its volume is open. Two galaxies overlap, yet their stars pass by one another. The visible intensity of a structure tells us how much light reaches us, not how much of its volume is filled with matter. This is also true of spiral arms. In photograph, they appear as bright curved lanes wrapping around the galactic center. They can look like fixed rivers of stars with wide empty spaces between them. But spiral arms are not rigid structures made from the same permanent group of stars. They are regions where matter becomes temporarily more concentrated and where star formation is more active. Gas entering an arm can be compressed. Molecular clouds form more readily. New stars ignite, including massive blue stars that shine with great intensity. These young stars make the arms visible. They do not remain young for long. The most massive ones live briefly and end before traveling far from their birth regions. Their light traces recent star formation, creating the bright patterns seen across spiral galaxies. Older stars pass into and out of the arms. The Sun does the same as it follows its long orbit through the Milky Way. A spiral arm is less like a permanent wall and more like a region of changing density through which stars and gas move. The traffic slowdown offers a useful comparison. Cars enter a crowded section, remain there for a time, and then continue forward. The slowdown persists even though the individual cars are constantly changing. In a spiral arm, the material is not stationary. Gas arrives, compresses, forms stars, and moves onward. The brightest young stars mark the arm for a while older populations spread more evenly through the disk. So even the Milky Way's most recognizable features are patterns within emptiness. The bulge is a denser pattern. Globular clusters are compact patterns. Spiral arms are moving patterns. Galaxy mergers are patterns being broken and rebuilt. None of them fill space in the way a solid object does. They are arrangements of isolated masses connected by gravity, light, and time. From a resting place beneath the night sky, these structures are compressed into a few degrees of vision. A star cluster becomes a small hazy patch. A distant galaxy becomes a faint oval. The Milky Way becomes one pale band. The distances disappear from sight, but they remain inside every image, holding the stars apart while allowing their light to gather. And beyond those lights, another structure surrounds the galaxy, far larger than the disk and almost completely invisible. It contains most of the Milky Way's mass, yet no telescope can photograph it directly. The luminous Milky Way is only the inner part of a much larger structure. The disk, the bulge, the spiral arms, and the scattered stars of the halo are the portions that reveal themselves through light. Beyond them extends a broad gravitational region that cannot be photographed in the same way. Astronomers call it the dark matter halo. It surrounds the visible galaxy in a roughly spherical distribution, reaching far beyond the bright stellar disk. The stars and gas we see are embedded inside it, moving through a gravitational field shaped by matter whose nature remains unknown. Dark matter does not glow. It does not reflect starlight or absorb light in any familiar way. It has not been collected in a container or observed as a visible cloud. Its presence is inferred from gravity, from the way galaxies rotate, bend light, gather into clusters, and behave during collisions. The first clue can be found in orbital speed. Within the solar system, planets farther from the Sun generally move more slowly than planets closer in. Mercury travels quickly because it is deep within the Sun's gravitational field. Neptune moves more slowly because it orbits far beyond most of the solar system's mass. A similar pattern was once expected in galaxies. If most of a galaxy's mass were concentrated where most of its light appeared, then stars near the outer edge should orbit more slowly than stars closer to the center. But that is not what astronomers found. Measurements of spiral galaxies showed that stars and gas far from the center often moved nearly as fast as material closer in. Their orbital speeds remained high across regions where the visible matter had already become thin. The curves describing those speeds stayed unexpectedly flat. Something was providing additional gravity. The unseen mass could not be confined to the bright central regions. It had to extend outward through a much larger volume, surrounding the visible galaxy in a halo. The Milky Way follows the same broad pattern. The Sun travels around the galactic center at hundreds of thousands of miles per hour. It completes one orbit in roughly 230 million years, following a path determined by the combined mass of the bulge, disk, gas, stars, dark matter, and the other components distributed throughout the galaxy. The Sun is not being pulled only by what shines. Much of the gravity shaping its motion comes from material that produces no light. This changes the meaning of emptiness. A region between stars may contain almost no ordinary matter, yet it still lies inside the dark matter halo. Space that appears vacant can carry a gravitational influence produced by an unseen distribution extending through and beyond the entire galaxy. Dark matter does not gather into stars, planets, or solid clouds in the way ordinary matter does. Whatever particles make it up, they appeared not to interact strongly through the electromagnetic force. They do not readily collide, radiate energy, or cool into a thin rotating disk. Ordinary gas can lose energy. Clouds collide. Atoms emit radiation. Material settles toward the galactic plane and becomes concentrated into stars. Dark matter cannot shed energy in the same way. It remains spread through a broad halo, moving on many intersecting paths. This difference helps explain why the luminous Milky Way forms a flattened disk while most of its dark matter surrounds it in a more extended shape. The disk is what cooled and settled. The halo is what remained diffuse. The scale of that halo is difficult to define because it has no sharp outer edge. Its density declines gradually with distance from the center until the Milky Way's influence begins to blend with the surrounding environment and the gravity of neighboring galaxies. The visible disk spans more than 100,000 light years. The dark matter halo extends several times farther. This means the object we call the Milky Way occupies far more space than the familiar spiral shown in diagrams. The spiral is the illuminated center of a much larger gravitational system. Far outside the stellar disk, a traveler might see the galaxy as a distant band behind them. The stars would become sparse. The thin gas of the disk would fade. Globular clusters and isolated halo stars would appear only occasionally. Yet the traveler would still be inside the Milky Way's dark matter halo. There would be no visible boundary to cross. The change would be gravitational rather than visual. A gradual weakening of the galaxies hold across tens and hundreds of thousands of light years. This extended halo helps keep the outer regions of the Milky Way bound. Without additional unseen mass, the observed motions of stars and gas would not match the gravity produced by visible matter alone. Some outer material would be moving too quickly to remain in the arrangement we observe. Dark matter provides the deeper gravitational well. It gives the visible galaxy a larger foundation than starlight suggests. The idea did not arise from one measurement. Astronomers have found several independent signs of missing mass. Galaxy clusters contain galaxies moving too rapidly to be held together by visible matter alone. Their gravity bends the path of background light more strongly than their stars and gas can explain. The large-scale structure of the universe also develops in ways that fit a cosmos containing far more matter than telescopes can directly see. Together, these observations support a model in which dark matter accounts for most of the matter in the universe. Ordinary matter remains the smaller share. Every star, planet, cloud, human body, grain of dust, and atom of interstellar gas belongs to that visible minority. This does not mean dark matter has been completely understood. Its gravitational effects are clear, but its physical identity has not been established. Many candidate particles have been proposed. Experiments have searched for rare interactions between dark matter and ordinary matter, while telescopes have looked for indirect signs that some dark matter particles might decay or destroy one another. No single candidate has yet provided a confirmed answer. So, there is a careful distinction to keep. The evidence for unseen gravitational mass is strong. The question of what that mass is remains open. This uncertainty does not make the halo less important. It simply means that one of the largest components of the Milky Way is known mostly through what it causes. A leaf moving across water can reveal a current that cannot be seen directly. In a similar way, the motion of stars reveals the structure around them. Their orbits trace gravity. Their speeds expose missing mass. Their distribution places limits on the halo shape. Streams of stars are especially useful. When a globular cluster or small satellite galaxy is slowly pulled apart by the Milky Way, its stars can spread into a narrow arc around the galaxy. These stellar streams preserve a record of their former orbits. As they move through the halo, they respond to its gravitational field. A smooth halo produces one kind of path. Uneven concentrations of matter can bend, widen, or interrupt the stream in other ways. By mapping these long ribbons of stars, astronomers can study a structure that remains invisible. Some streams stretch across large portions of the sky. They are the remains of systems the Milky Way gradually dismantled. Their stars once moved together inside clusters or small galaxies. Galactic tides drew them out, arranging them into extended trails. The streams are faint, but they are valuable. They turn the halo into something measurable. Satellite galaxies provide another clue. The Milky Way is accompanied by smaller galaxies that orbit within its larger gravitational domain. The Large and Small Magellanic Clouds are the most prominent examples from the southern sky, but many fainter companions have also been found. Their positions and motions help astronomers estimate the Milky Way's total mass. This is not a simple measurement. Some satellites may be on their first approach. Others may have completed several orbits. Their paths have been altered by the Milky Way, by one another, and by the gravity of the nearby Andromeda galaxy. Different methods can therefore produce different estimates. The exact mass and outer boundary of the halo remain under study, but the overall conclusion is stable. The unseen component is much more massive than the visible stars and gas alone. And within that halo, ordinary matter becomes sparse in a second way. The stellar halo contains old stars, globular clusters, and debris from earlier mergers, but they occupy only a tiny fraction of the available space. A thin atmosphere of hot gas also surrounds the Milky Way, extending well beyond the disk. This gas can reach temperatures of hundreds of thousands or millions of degrees, yet it is so diffuse that its total heat transfer would remain weak. Individual particles carry high energy, but they are separated by large intervals. The hot halo is difficult to detect directly. Astronomers observe it through faint X-ray emission and through the way it absorbs selected wavelengths of light from distant sources. Its full mass and shape are still being refined. Some of the ordinary matter associated with the Milky Way may reside in this extended, hard-to-see gas. The galaxy's apparent emptiness therefore contains several overlapping layers. There is interstellar space between stars in the disk. There are cavities carved by stellar winds and supernovae. There is the sparse stellar halo above and below the disk. There is thin hot gas extending much farther outward, and through all of it lies the dark matter halo, unseen. but gravitationally dominant. These components occupy the same broad region without filling it in the ordinary sense. Dark matter may pass through Earth and the Sun without noticeable contact. Halo gas drifts at density far below anything familiar. Stars remain divided by large distances. The galaxy is held together not because its parts touch, but because gravity does not require contact. Every mass alters the geometry around it. Across thousands of light years, those small contributions join into one galactic field. Across larger distances, the halo becomes the principal source of attraction. The visible Milky Way moves inside that field like a bright pattern held within a transparent sphere. This large structure also connects the galaxy to the cosmic web. Dark matter does not exist only around isolated galaxies. It forms filaments, knots, and halos across the universe. Galaxies developed inside the densest portions of that structure, where gravity had gathered both dark matter and ordinary gas. The halo of the Milky Way is one local part of a much older pattern. Its foundation began before the first stars formed. Ordinary matter fell into gravitational wells built largely by dark matter. Gas collected, cooled, and produced the luminous galaxy. The unseen structure arrived first, and the stars followed. So the Milky Way's emptiness is not unsupported. It has an invisible architecture. The bright disk may appear to float in space, but its motion is carried by a halo that extends far beyond the last obvious stars. What seems empty to the eye can still guide orbits, bend trajectories, and hold an entire galaxy together. And beyond the outer reaches of that halo, the gaps widen again. The Milky Way gives way to intergalactic space, where galaxies themselves become isolated islands and emptiness expands from light years into millions of light years. Beyond the Milky Way's outer halo, the scale of emptiness changes again. The nearest large galaxy, Andromeda, lies about 2.5 million light years away. Between the luminous disks of the two galaxies stretches a region far larger than either galaxy itself, crossed by thin gas, dark matter, faint dwarf galaxies, and the occasional star moving without an obvious home. There is no clear wall where one galaxy ends and the space between galaxies begins. The Milky Way's outer halo thins gradually. Andromeda's halo extends outward in the opposite direction. Their gravitational domains may reach farther than their visible stars suggest, and the material between them belongs to a larger system called the local group. The local group contains dozens of galaxies. Most are small dwarf galaxies, faint systems with far fewer stars than the Milky Way or Andromeda. Some orbit the larger galaxies. Others move through the shared gravitational field of the group. Together, they occupy a region roughly 10 million light years across. That sounds like a crowded neighborhood only because the word group suggests closeness. On galactic scales, the members are connected by gravity. On the scale of any traveler, they remain separated by journeys lasting millions of years at the speed of light. If the Milky Way were reduced to the size of a dinner plate, Andromeda would sit several meters away. The dwarf galaxies would appear as smaller marks scattered through the surrounding room. Most of that room would contain no galaxy at all. The same pattern continues outward. The local group is only one small gathering within a far larger arrangement of galaxy groups and clusters. Some clusters contain hundreds or thousands of galaxies held together by gravity. Between the clusters run long filaments of matter, extending across hundreds of millions of light years. Together, these filaments form the cosmic web. In large maps of the universe, galaxies do not appear evenly scattered. They trace walls, strands, branching structures. Dense nodes form where several filaments meet. Between them lie broad regions containing very few galaxies. These are the cosmic voids. A void is not an empty bubble with a sharp boundary. Its matter density is simply much lower than the cosmic average. A few faint galaxies may exist inside it. thin gas and dark matter remain present, but compared with the filaments, a void has lost much of its material to surrounding regions. Gravity created both. In the early universe, matter was distributed with great uniformity, but not perfect uniformity. Slightly denser regions pulled in more material. Slightly thinner regions lost matter to their neighbors. As the universe expanded, the contrast increased. Dense regions grew into halos, galaxies, groups, and clusters. Underdense regions expanded more freely and became voids. Matter flowed away from their interiors toward the walls and filaments around them. The result is a universe organized less like a field of scattered objects and more like a network. Galaxies gather along the network's threads. The open volume between those threads occupies most of space. This is a larger version of the pattern already seen inside the Milky Way. Within the galaxy, stars occupy a small part of the disk, while most of the volume lies between them. Within the universe, galaxies occupy the filaments and clusters, while most of the volume lies in the voids. At each scale, gravity concentrates matter without filling space. The more closely matter gathers in one place, the more open another region becomes. This gives cosmic emptiness a history. A void is not merely a place where nothing happened. It is a region whose matter gradually moved elsewhere. Its low density records the long pull of surrounding structure. The galaxies lining a void's boundary are part of that record. They mark the directions in which matter flowed. Dark matter played a central role in this growth. Before ordinary gas could cool into stars, dark matter had already begun forming an invisible framework of halos and filaments. Gas fell into those gravitational wells, collected, heated, cooled, and eventually produced galaxies. The luminous cosmic web follows, an older unseen one. Even now, much of the material in the filaments cannot be detected through ordinary starlight. Some is dark matter. Some is extremely thin gas, heated to temperatures that make it difficult to observe. Astronomers search for this gas through faint X-ray emission and through small absorption features left in the light of distant objects. The matter is sparse, but across millions of light years it can add up. This is another reminder that emptiness depends on perspective. A single cubic meter of intergalactic space may contain almost nothing. A filament spanning hundreds of millions of light years may still hold an immense total mass. Density and total amount are not the same. A mist can be thin and still cover a continent. The cosmic web can be diffuse and still guide the formation of nearly every galaxy we see. Within a rich galaxy cluster, the space between galaxies contains hot gas heated to millions of degrees. That gas can outweigh the visible stars in the cluster, even though it remains far too thin to resemble an atmosphere. The cluster is also embedded in a large dark matter halo. The galaxies move through this shared environment, orbiting the cluster's center and occasionally passing near one another. Their gas can be stripped away by the hot medium. Their shapes can change through repeated gravitation encounters. Yet, even a cluster filled with thousands of galaxies remains mostly open volume. The galaxies themselves rarely collide as solid bodies because galaxies are not solid bodies. When two overlap, their stars pass through broad spaces. When two clusters meet, their galaxies and dark matter can move through the encounter while their hot gas collides, slows, and heats. Different components behave according to different forms of interaction. Gas feels pressure. Stars respond mainly to gravity. Dark matter appears to pass through with very little direct resistance. A single collision can therefore separate the visible gas from the dominant gravitational mass, revealing the hidden structure through its effect on background light. The universe becomes readable through these separations. Matter that cannot be seen is traced by gravity. Gas that is too thin to photograph directly is traced by radiation, and voids are traced by what is missing. The cosmic web is reconstructed from millions of galaxy positions. Each one a bright marker inside, a structure far larger than itself. Seen from the surface of Earth, none of this arrangement is apparent. The night sky appears almost flat. Stars lie across one dark surface. A few galaxies appear as faint patches. Distance is hidden because light from objects at vastly different depths reaches the eye together. But the sky is not a ceiling. It is a view through layers. One star may be tens of light years away. Another may be thousands. A faint galaxy may be millions of light years beyond both. Behind it may lie a galaxy cluster whose light began traveling before complex life existed on Earth. The dark interval between visible points is not one continuous backdrop. It contains the full depth of the universe. At this moment, light is crossing those intervals from every direction. Some photons have traveled for minutes. Some have traveled for billions of years. They pass through galactic disks, outer halos, filaments, clusters, and voids before arriving at a mirror, a detector, or a human eye. The emptiness preserves the journey in a dense material. Light is scattered, absorbed, or transformed. In the thin spaces between galaxies, it can travel for immense spans with little interruption. That is why distant galaxies remain visible. The universe is open enough for old light to survive. The same emptiness that separates us from remote structures also allows us to study them. A telescope does not reach outward and touch a galaxy. It receives light that has already crossed the distance. Astronomy depends on the openness of space. Each observation is possible because the path remained clear enough for information to arrive. There is a calmness in that arrangement. A galaxy may be beyond reach, yet its light is not absent. A cluster may lie across a void, yet the space between does not erase it. Distance delays the message, but it does not always prevent it. While you rest beneath one small part of the Milky Way, ancient light continues, moving through the larger structure around it. It crosses regions where galaxies are scarce, passes along the edges of filaments, and enters the halo of our own galaxy before reaching the solar system. The journey may have begun before Earth formed. A photon arrives without carrying the distance in any visible form. It appears only as a faint point, a slight glow, or a mark on a detector. But inside that small arrival is a path through cosmic emptiness. The voids are not obstacles placed between meaningful places. They are part of the structure itself. Without underdense regions, there would be no contrast from which filaments could emerge. Without the movement of matter away from some regions, there would be no great concentrations in others. The emptiness and the galaxies belong to the same history, and that history is still unfolding. The universe continues to expand. Galaxy groups not bound to one another are carried farther apart. Voids grow wider as matter remains concentrated along their edges. The cosmic web persists, but its isolated regions become more isolated with time. To understand where this leads, the view must move from space into time. The Milky Way is almost empty now. Its distant future will reveal whether that condition is temporary or whether emptiness is the direction in which the galaxy has been moving all along. The Milky Way is open in space, and it is also open in time. Nothing in the galaxy keeps the same neighbors forever. Stars move along their own paths around the center, rising above and below the disk, passing through spiral patterns and gradually changing their positions relative to one another. The Sun travels around the Milky Way at roughly 230 kilometers per second. Even at that speed, one orbit takes more than 200 million years. During a single galactic year, continents can separate, oceans can open and close, species can appear and disappear, and the constellations can be rearranged beyond recognition. The stars seem fixed only because a human life is brief beside their motion. Over thousands of years, the changes remain subtle. Over hundreds of thousands of years, familiar patterns begin to bend. Over millions of years, many constellations dissolve completely as their stars move along different paths through the disk. The night sky belongs to one moment in the galaxy's motion. The Big Dipper, Orion, Cassiopeia, and the Southern Cross are temporary arrangements created by perspective. Their stars are not traveling together in most cases. They lie at different distances and move in different directions. From another part of the galaxy, the same stars would form no recognizable shape. From Earth, they appear connected because the eye flattens depth into a single dark surface. Time slowly reveals the depth again. Some nearby stars are approaching the solar system. Others are moving away. In tens of thousands of years, a different group will define the local neighborhood. The nearest star beyond the Sun will not always be Proxima Centauri. A star called Gliese 710 is expected to pass through the outer region of the solar system in the distant future, coming much closer than most neighboring stars do today. It will still remain far beyond the planets, but its gravity may disturb some comets in the Sun's distant cloud. Such passages are part of ordinary galactic motion. They are uncommon on human timescales and common across the age of a star. The Sun has already experienced many distant encounters during its journey around the Milky Way. Most left the planets unchanged. Some may have altered the paths of remote comets. The openness between stars kept the inner solar system protected through almost all of them. The galaxy changes through these small exchanges. Stars enter new neighborhoods and leave old ones. Clusters disperse, streams stretch around the halo. Gas clouds gather, fragment, and disappear. Spiral patterns shift as matter moves through them. There is no permanent map. Even the Milky Way's broad shape evolves. Its disk continues to gather some gas from the surrounding environment. At the same time, stellar winds and supernovae drive material outward. Some gas escapes into the halo. Some cools and falls back, creating a slow circulation between the disk and the space above it. Astronomers sometimes describe this movement as a galactic fountain. Massive stars heat nearby gas and push it away from the disk. The rising material expands and cools. Gravity may then draw part of it back, carrying newly formed elements into other regions of the galaxy. Carbon, oxygen, silicon, iron, and many other elements have traveled through cycles like this. They were formed inside stars, released into surrounding space, mixed with older gas, and gathered into later generations of stellar systems. The matter inside Earth has moved through this larger circulation. Atoms now held in oceans, rocks, air, and living cells were once scattered through interstellar space. Some were forged in stars that disappeared before the Sun began to form. They crossed open regions of the galaxy as gas or dust, entered a molecular cloud, and became part of the solar system. The emptiness between stars was not an interruption in that history. It was the medium through which the material traveled. A dust grain does not need the galaxy to be crowded. It needs time, motion, and a path into a region where gravity can gather it again. Across generations of stars, the Milky Way has slowly changed its chemical composition. The earliest stars formed mostly from hydrogen and helium. Later stars inherited small amounts of heavier elements produced by those that came before. With each cycle of birth and stellar death, some regions became more chemically enriched. This process helped make rocky planets possible. It also reduced the galaxy's supply of easily available, star-forming gas. Not all gas returns to the interstellar medium. Low-mass stars can hold material for billions or trillions of years. White dwarfs, neutron stars, and black holes lock away part of the matter that once moved freely through clouds. Some gas is expelled from the galaxy. Some becomes too hot or too diffuse to collapse readily. The Milky Way still forms stars, but it does so more slowly than many younger galaxies did in the distant past. Its most intense period of stellar production has already passed. In the future, star formation will continue to decline. Molecular clouds will still appear. New stars will still ignite, but the rate will gradually fall as usable gas is consumed, heated, dispersed, or confined inside long-lived objects. The bright blue stars will disappear first. They burn through their fuel quickly, surviving for only millions of years. New ones will replace them for a time, but as star formation weakens, their blue light will become less common. Stars like the Sun last much longer. The Sun is about halfway through its main hydrogen-burning life. In several billion years, it will expand into a red giant, release its outer layers, and leave behind a white dwarf. That future remnant will not shine through fusion. It will glow from stored heat, cooling over spans far longer than the Sun's present age. The smallest red dwarfs will remain active much longer. They use their hydrogen slowly and can continue shining for trillions of years. Long after stars like the Sun have become remnants, red dwarfs will provide much of the remaining starlight. The future Milky Way will grow dimmer in stages. First, the shortest-lived stars will vanish, then the medium-sized stars will fade. Red dwarfs will continue through an age far beyond any era the universe has yet experienced. Around them, the galaxy will remain spacious. The distances between stars will not suddenly close. Some objects will be lost through gravitational encounters. Others may settle toward the center or be sent into wider orbits. The galaxy will be rearranged, but it will not become full. Its open structure will persist after most visible light has gone. White dwarfs will cool toward the temperature of their surroundings. Neutron stars will continue turning with weakening magnetic fields. Black holes will move through the darkened system, sometimes alone and sometimes in binaries. Occasional encounters may still occur. Two remnants might merge. A star could be disrupted near a black hole. A surviving planetary body might pass close enough to another object to change direction. But these events will be isolated across immense intervals. The later galaxy will contain less activity and more waiting. Cosmic expansion will also alter the wider view. The Milky Way and the galaxies gravitationally bound to it, which can remain together despite the expansion of the universe. More distant groups, however, will continue receding as space between them grows. Over enormous spans of time, their light will become increasingly redshifted and faint. Eventually, remote galaxies may pass beyond what future observers can detect. A civilization living in that distant era could see only the merged remnant of the local group and the darkness beyond it. The cosmic web, visible to present-day astronomers, would no longer appear in the sky. Evidence of the wider universe would become harder to recover. The background radiation from the early cosmos would stretch to wavelengths, increasingly difficult to observe. Distant galaxies would disappear from view. The local structure would seem more isolated than it truly was. That future sky would not reveal the universe's history as openly as ours does now. We live during an interval when ancient light remains accessible. Telescopes can observe young galaxies, measure the early universe, map the cosmic web, and follow the expansion of space. The messages have not yet faded beyond reach. Generations before modern astronomy looked upward without knowing how far the light had traveled. Generations after us may build instruments that see more clearly than anything available today. For this period, the universe remains readable. The darkness between objects has preserved enough light for the story to arrive. And while the Milky Way slowly changes around us, the present sky holds one temporary arrangement of stars' gas, dust, and distant galaxies. It will not remain this way, but for now, its open spaces are still crossed by light. The Milky Way has never been empty in the simple sense of containing nothing. It holds stars, planets, clouds, magnetic fields, radiation, stellar remnants, streams of ancient debris and a dark matter halo extending far beyond the visible disk. It carries the remains of older galaxies and the raw material of stars that have not yet formed. Every part of it is moving through gravity, and still, almost all of its volume is space. That apparent contradiction disappears when scale is allowed to return. A star can be larger than 1,000,000 Earths and still occupy only a minute point inside its galactic neighborhood. A molecular cloud can span dozens of light years and remain thinner than the best vacuum chambers on Earth. A galaxy can contain hundreds of billions of suns and still allow two galaxies to pass through one another with very few stellar collisions. The Milky Way is not a solid thing in the way a planet is solid. It is a pattern of motion. Its shape comes from orbit. Its spiral features come from changing regions of density and star formation. Its central bulge is a gathering of old stellar paths. Its halo preserves stars and fragments from systems absorbed long ago. Its dark matter cannot be seen, yet provides much of the gravity that holds the visible structure together. What looks like an object from far away becomes a landscape of separations from within. The same is true of the night sky. The pale band overhead does not mark a wall of stars. It is a long view through the disk, where many distant points overlap along one line of sight. The glow becomes continuous only because the eye cannot keep each star separate across such distance. Between those points are intervals that light takes years to cross. Those intervals are not mistakes in the design of the galaxy. They are part of what allows the galaxy to work. Because stars are far apart, planetary systems can remain stable for billions of years. Because gas is diffuse, it can be stirred, compressed, heated, and gathered again into new clouds. Because space is open, light can travel from distant stars and galaxies without being erased by constant collisions with matter. The emptiness protects, connects, and preserves. It protects worlds from frequent close encounters. It connects remote places through light and gravity. It preserves old information, allowing a photon to leave a galaxy long ago and arrive at a telescope now. Nothing in this arrangement is static. The sun continues around the galactic center. Nearby stars move along their own paths. Clouds gather and disperse. Clusters loosen. Stellar streams lengthen across the halo. The Milky Way Andromeda continue through the shared gravity of the local group. Will pass. Yet the underlying pattern will remain recognizable for a very long time. Matter will continue to gather into small concentrations while most of the surrounding volume stays open. Stars will continue to be islands rather than a continuous sea. Far in the future, fewer new stars will form. The bright young populations will become rare. Long-lived red dwarfs will carry starlight into ages the universe has not yet reached. White dwarfs will cool, neutron stars will spin more slowly. Black holes will remain in regions where ordinary light has faded. The galaxy will become darker without becoming smaller in the same proportion. Its old orbits will continue through a structure increasingly defined by remnants and distance. Even then, gravity will cross the gaps. A dark star remnant will still respond to masses far away. A surviving planet may continue circling a dim object. A distant encounter may change an orbit after billions of years of stability. The galaxy will never need its parts to touch in order to remain a galaxy. That may be the most useful way to understand its emptiness. The open space is not outside the structure, it is the structure. The distances determine how often stars meet, how long planetary systems survive, how gas moves, how clusters dissolve, and how the galaxy changes over time. Remove the distances, and the Milky Way would not become a fuller version of itself. It would become something else entirely. A dense collection of stars would produce more encounters, more disruption, and less long-term stability. A disk without thin gas would lose the material needed for future stars. A universe without broad voids would not develop the same filaments, groups and clusters. The spaces between things help give the things their form. This idea continues downward as well as outward. Within ordinary matter, atoms are separated by regions that are not filled with smaller solid pieces. Their behavior is governed by fields and forces. The sense of solidity comes from interactions, not from matter occupying every point. At human scale, a table feels continuous. At atomic scale, it is an arrangement. At galactic scale, the Milky Way is also an arrangement, though its intervals are measured in light years instead of fractions of an atom. The difference is size, not principle. Matter gathers. Forces connect, space remains. You do not need to hold the full scale in your mind. No image can contain it accurately. No comparison can make 4 light years feel ordinary. The numbers can guide understanding, but they cannot reproduce the experience of distance. It is enough to notice what the darkness between stars represents. It is not a blank surface behind the sky. It has depth. Beyond one visible star may lie years of open space, another stellar system, a cloud too faint to see, the outer halo, another galaxy, and then a void extending far beyond any journey humanity has begun. The black portion of the sky is not empty of history. Light has crossed it from exploding stars, cooling clouds, orbiting planets, and galaxies whose shapes have already changed. Some of that light is still traveling. Some will never arrive here. Some is passing Earth at this moment and continuing outward. The galaxy remains almost empty, yet it is never without motion. Even where there is no nearby star, gravity still curves paths. Magnetic fields guide charged particles. Thin gas carries the products of earlier suns. Radiation moves from one region to another. The quietest parts of the Milky Way still belong to its story. And here, around one ordinary star in the outer disk, matter has gathered into a planet with oceans, air, stone, and living minds able to notice the intervals around it. That gathering did not happen in spite of the emptiness. It happened within it. The distance from neighboring stars gave this system time. The remains of earlier stars supplied its elements. The open path of light revealed the larger universe. The galaxy's sparse architecture allowed one small world to remain in orbit long enough for awareness to appear. Above that world, the Milky Way continues across the sky. Its glow comes from countless suns, its darkness comes from the room between them, and both belong to the same galaxy. The space between the stars keeps the light apart.